Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're not tackling a problem, but rather deriving this equation, this famous position equation that you were taught in school, but not necessarily know where it comes from, right? What does this equation say? This equation says that the position at any given time will be equal to the original position plus the original velocity times the time that I'm interested in, plus the acceleration times the time squared over 2. So if I want to know the position at time equals 3 seconds, I would take the original position, it does not change. I would take the original velocity that does not change and multiply that by 3. I would take the acceleration, that in this case does not change, and I'll multiply that by 3 squared and divide the whole thing by 2. Where does this originate from? Well, as always, we're going to start from the very basics, very fundamentals, and we're going to go from there. The very fundamentals are, what is velocity and what is acceleration? And we're going to start with those two things, and from there we're going to be able to derive the equation, right? So the velocity, definition of velocity, is how the position changes with time, right? It's a vector that is trying to measure how a given object's position is changing with time. And the acceleration is how the velocity is changing with time, right? So again, these are the fundamentals. And we only need to know this and some basic calculus to be able to get to our final equation. So let's start with this equation right here. Let's go ahead and say that if that's the case, then velocity times dt will be equal to dx, right? And as a matter of fact, we leave x on the left-hand side. Okay? So if we are to integrate this, and we integrate on both sides of the equation, we are able to expand this, and there's two ways of doing it. You can do, the integration with the defined integrals from where to where, or you can leave it as undefined. Whatever rocks your boat, let's do both here just for the sake of your understanding. So let's start with the general one. The general one is going to say, okay, so the integration here is going to be x plus a constant, right? And on the right-hand side, we're going to have that the integration is going to be v times t plus a constant. But there's a very big but here. This integration is only true if my velocity is not a function of time, right? This is only true if my velocity is not a function of time. Because if it is a function of time, then this is not true. So let's write that down because this is super important, okay? Let's write it down. If velocity is not a function of time, then therefore the ratio here is going to be velocity times the time will be equal to the difference in position, right? If we're going from a time of 0 all the way to t, from a position of original position all the way to any position that I want. So if it's not a function of time, then this velocity here does not care about this integral. It leaves the integral, and I'm only integrating dt, right, which is going to give me time. Beautiful. If that's the case, then I have this, and this leads to our very simple equation that says that velocity will just be equal to the change in position divided by time. This is great, and this can be used whenever we don't have the velocity changing in respect to time. Or another way to think of this is you can always use this when there's no acceleration, right? When the velocity is constant. Simple equation, very straightforward. But, however, if a velocity does change in respect to time, then I'm going to have to take a step back and think about this, because if my velocity is a function of time, then I can solve this integral normally, but then when it comes to this integral here, I cannot solve it unless I know how my velocity changes with time. And that's where the acceleration, the idea of acceleration, comes in and helps us out, right? So if my velocity is a function of time, then here on the left-hand side, I'm still going to have, my same integral, and here I'm going to have my same integral, but I cannot go ahead and solve this right off the bat. I need to have the way that velocity is changing with time. Okay, and how do I do that? Well, I go to the fundamental of acceleration, because acceleration is precisely measuring how my velocity is changing with time. And once again, here we're going to have something very interesting, because let me put here on the corner so they can go back afterwards. Because the idea is going to be exactly the same. I'm going to do, okay, my acceleration times dt equals my dv, and I can integrate on both sides of the equation. But here's the interesting thing, in my opinion. If the acceleration is a constant now, we can solve this just like we did before. If it's not a constant, then we cannot, right? So that already tells us something about the equation we're trying to find out, which is this one. This is only valid, this can only be used when my acceleration is a constant, right? That's one of the restrictions there. My acceleration is not a constant, then you cannot use this. Right, so let's go ahead and solve this. Straightforward. We're going to go from 0 to t, and we're going to go from v naught. So from define integral from 0 to t, and here from v naught to v. Note that once I do that, I'm already doing a boundary condition, right? I'm saying that when time is 0, my v is v naught, or initial velocity. And here, because my acceleration does not care, it's just going to come out of the integral, and I'm going to be left with t minus 0. And on the right-hand side, I'm going to be left with v minus v naught, which tells me that, and I'm going to solve this for velocity, not for acceleration. Solve for velocity. It tells me that my velocity is equal to the acceleration times the time plus my v naught. And this is exactly what I'm looking for, because now I know how my velocity is changing in respect to time. And if you recall, that's what we needed to be able to solve the integral we had before, right? So all I'm going to do now is I'm going to copy this and copy the whole thing. Copy the whole thing, right, which is equal to v. And I'm going to come here and say, okay, I now know that v is equal to this whole thing. So therefore, where I have v, I can substitute by this thing, and therefore I'm going to have, if I integral from 0 to t dt, will be equal to the integral from x naught to x dx. Once again, note that I'm already putting a boundary condition here. I'm saying that when my time is 0, my position is my x naught, or my position, my original position. Okay, and now this integral is simple to do. Note that we're now multiplying the sum here by dt, so we're going to have to expand on this. On the left-hand side, this is just going to be x minus x naught. And on the right-hand side, I'm going to have the integral from 0 to t of at dt plus integral from 0 to t of v naught dt. This is where it gets interesting, because the integral of the acceleration is trivial, right? It doesn't really care about the time. The acceleration is a constant, as defined in the beginning. So this is just going to be acceleration times the integral of t dt, and that's going to be t squared minus 0 squared over 2, right, as we go from t to 0. And over here I'm going to have, again, this v naught does not change with time, right? It does not care of time. It doesn't matter if the time is 10, 100, or infinity, my v naught is always going to be the same. It's a fixed velocity. So therefore it comes out of the integral, and I'm only integrating dt. And dt is just going to be t minus 0. Obviously the zeros go away, and they're not going to be doing anything here, and we're left with a t squared over 2 plus v naught t. And this is almost there, right? The only thing that I'm missing is just to rearrange this equation and sum x naught on both sides. So I'm going to have x equals x naught, I'm summing on both sides, plus my v naught times t plus my acceleration t squared over 2. And that is exactly the equation we were trying to derive. Beautiful. So what are the other ways of doing this? Well, if you recall, the other way we can do it, if we do the integration in the without defining it, which is what I promised I'll do too, is check it out. So I'm going to go solve the same integration for the case that the velocity is not a function of time. Okay, so I'm going to do the integral of dx undefined equals the integral of v dt undefined. And what this is going to give me is, this is going to be x plus a constant, any constant, will be equal to my v, again it comes out of the integral, times t plus another constant. We have two constants here, they can be summed up, and we can remove one of them because a constant plus a constant is going to be a constant, or a constant minus a constant is going to be a constant. So I'm going to go ahead and say, okay, this is the same thing as x equals vt plus a constant, right? And to be able to go from here to here, all we need is to eliminate that constant. And for that, I need a boundary condition, and I'm going to say that at time equals 0, my position equals x naught, right? Because that's precisely the definition of x naught. X naught is, what is the position x when my time is 0? Okay, that's all. And if I do that, what ends up happening is, I'm going to say, okay, if my x is x naught at 0, then that means that this is going to be x naught, v times 0 plus my constant. V times 0 is 0, and therefore x naught equals my constant. If x naught equals my constant, then I can go back here and say, okay, so therefore x will be equal to v times t plus x naught. Because we just found out that c equals x naught. And therefore you can see that this is now the same as we had before. This is, we can do x minus x naught equals v times t. Therefore, v will just be my delta x divided by t. So you can always do it this way too, without defining the integral, and then doing boundary conditions to eliminate the constants later. You're always going to get the same result. The interesting thing about this is, as I pointed out during the derivation, is that when you're doing the defined integral, you're actually doing exactly this kind of thing here, but just on a subtle way, right? So when you have, where is it? Right here. When you have the definition of the integral from 0 to t, and the definition of the integral from x naught to x, basically what we're saying is, when time is 0, x is x naught. So you're already doing that, but just in a different way, right? Likewise, when you do the integration of the acceleration, right here, you're saying that when time is 0, your v is your v naught, your initial velocity. So with that, we, from the fundamentals, we arrived at the equation that we wanted to arrive. I think this is an excellent exercise if you want to do on your own to really try to get a better understanding of where this comes from and how to use it. When we do this, we see a couple of things that are important. For instance, we see that this equation can only be used when my acceleration is constant, right? Because it comes from this integration here, which assumes the acceleration to be constant and therefore to be able to leave that integration. If my acceleration is not constant, then we need to know what is the way acceleration changes with time, and then we need to integrate that into the equation. What else do we learn by doing this? We learned that the position, the original position, the velocity is not a function of time, right? If the velocity is a function of time, then that's when we get this equation here. So if velocity is not a function of time, then we get the simplified version here. And note that if I go here and I say, my velocity, original velocity is 0, then this also becomes simplified, right? Because my original velocity is 0, there's nothing moving, and this goes to 0, and therefore I'm left with just this idea here of x equals x naught, and then how the acceleration changes with time. So that's another thing that we see when we do the whole derivation. What else? And I guess the last thing we can see is that because this is a relationship with that, then we can say that, okay, therefore the acceleration is the second derivative of position in respect to time, right? This is how this idea comes to be. This is a derivation of something that is a derivation. So a second derivative. All right. So I think that's all I had for you today. If you have any questions, leave down on the comments below. If this was helpful, consider leaving this video a like, and we'll talk soon.